Hello again and welcome to a new lecture in which we will discuss about stress blocks and internal moment in elements like beams, for example. Before we do that, let's look at an axially loaded member. An axially loaded member is like a straight member like the ones in a truss. So if we were to cut the member at a certain location and draw the free body diagram of the left hand side, that is what is pictured here in picture B, we will get something like this if we draw the member with its real cross section. So you can see the axial force, in this case equal to 1,800 newtons, acting along the longitudinal axis of the member. Now, at a certain distance along the member, away from where this force is applied as a concentrated force, the force will distribute it across the area G.25.i, and it will create a stress, an axial stress, which in this case will be a stress having a constant intensity, constant magnitude. So as we've learned before, this magnitude of the stress in this case will be equal to 1,800 newtons divided by the dimensions of the cross-sectional area, and that will give us 6 newtons per millimeter square, or 6 megapascals. So axial forces will always produce a uniform intensity axial stress. However, if we have something else than just the axial force on the cross section, maybe there's a combination of the axial force and some bending moment, then we will end up with a composite stress block. A stress block that is not constant anymore. It will have a certain type of variation, like for example this one in diagram A, where the load intensity or the stress intensity varies linearly from a magnitude of 12 megapascals at the top to a magnitude of 8 megapascals at the bottom. So how do we treat this? Well, remember, we need to find the location of F and its magnitude. It's easier if we divide this stress block into components, for example, into a constant load intensity component and a linearly distributed variable stress intensity component. So a rectangular component, a prism component, and a wedge component. For these components, we can easily then determine the magnitude of those two forces. So F1 will be equal to the volume of the prism, so 24 kilonewtons. F2 will be equal to the volume of the wedge, so in this case 6 kilonewtons. And of course, for equivalency, for the first condition of equivalency, the total force F must be equal to the summation of F1 plus F2. We also know the location of F1 and F2 based on the centroids of these pressure blocks as circled in these diagrams. In the end, we will need to find the location of the total force, and that's a little tricky because we do not know the centroid of this trapezoidally shaped volume in 3 dimensions. So again, for equivalency, the first equation is that the sum of the forces on diagram A equals to the sum of the forces on diagram B. So that's already satisfied by summing F1 and F2 will give us the magnitude of F equal to 30 kilonewtons. But also for equivalency, the sum of the moments, say I'm choosing about line AB on diagram A, must be equal to the sum of the moments about the same line AB on diagrams B. So that means the magnitude of F, 30 kilonewtons, times Y star equals to 24 kilonewtons times 50 millimeters in the first diagram B, plus 6 kilonewtons times 66.7 millimeters in the second diagram in B. So from here we can quickly solve from Y star, which will equal to 53.33 millimeters. So now we know both the magnitude and the location of F by applying the principles of equivalency. And this is how we deal with composite stress blocks when we are not sure about the geometry, the location of the centroid, but we can divide them into simpler figures. Finally, we can look at the stress block generated due to internal moment in an element, such as in a beam. So if we have just a bending moment in a beam, we will likely end up with a stress block that is made of two wedges like this one. At the top, the maximum load intensity is 20 megapascals in compression, and at the bottom 20 megapascals in tension. And each of these two stress blocks will have an equivalent concentrated force, C and T, and we can calculate the magnitudes of these concentrated forces by determining the volumes of the two stress blocks. So in this case, the total compressive force will be equal to 270 kilonewtons, and the total tension force will be also equal to 270 kilonewtons. So two forces that are equal, parallel, and opposite create a couple. And the forces are located 1/3 away of AB or AE respectively from the top or bottom of the beam. So that's 60 millimeters from the top and 60 millimeters from the bottom. So then the distance, the moment arm between them is 240 millimeters. Now, if we sum the forces in the horizontal direction, the total resultant force is 0. So there is no axial force on the section. P equals 0. So C plus T equals 0, or very, very importantly, the total compression force in this case equals to the total tension force. And that's for pure bending, where P is 0. There is no axial force. So now finally we can determine the magnitude of the moment M created by the couple of forces C and T. So that equals to the magnitude of the force times the moment arm, and that will give us a moment of 64.8 kilonewton meters. So as you can see, these stress blocks, as shown in this picture, are equivalent to a moment, to an internal moment in this member, in this beam member, of having a magnitude of 64.8 kilonewton meters. Now you see that the tension and compression stress blocks are actually indicated by arrows, but sometimes you might see these two wedge stress blocks drawn as shown here in turquoise. So basically the tension block could be flipped on the other side, or the compression block could be flipped on the other side. And there's nothing wrong with that. This is another representation of the same type of stress blocks. So either or, the meaning is the same. Line AD is the place where the stress is 0. So that location is also called the neutral axis. But about that, we will talk in the future lectures. And in the meantime, thank you very much for watching this one.